So during this COVID-19 period, perhaps you've had a little time at home to do home projects. And perhaps one of those is to build a deck. And so why is it so important to understand both the joints when building a deck and using power tools to build that deck?
There we go.
So as you can see there, it's very, very critical to make sure that you're using the right tools to build those tools to help put your deck together. So perhaps maybe you didn't have to build a deck this spring during the COVID-19 aspect, but most likely you've had an opportunity or an unfortunate opportunity to have a flat tire over the time. So again, we want to talk about how important it is to have a correctly fastened wheel lug nut. So hopefully you guys had a little chuckle, and I feel a little lighthearted now. But now I am very, very pleased to introduce Skip Young, one of our sales engineers with over 30 years experience in fastening and assembly, to present the fundamentals of bolted joints. Thank you very much, and take it away, Skip.
All right, thanks, Dave. Again, echoing Dave, thank you very much for joining us today for this Tool University event by Rhino Toolhouse. Today, in particular, we're going to focus on fastening technology, but as you can see in the bullet points, we do much more than this. Industry 4.0, augmented reality, error-proofing, collaborative robots, ergonomics, wearables, hardware and software, and of course, service and repair. Hopefully today, our learning objectives will be achieved, and these are: define the principles of a bolted joint, understand a bolted joint as a system, understand the function of bolted joints, define torque, define angle, define clamp load, and understand torque measurement. Along with this, there are very applicable ISO standards related to both torque tools as well as other tools, and also including hand torque wrenches. 5393 specifically focuses on power torque tools and that test method. ISO 6789 specifically focuses on hand torque wrenches like this. It's very intentional that ISO has two different guidelines for testing because those two are different from each other. Another one's very important is actually the accreditation of a lab, in this case 17025, which a Rhino Toolhouse is 17025 accredited. In addition, VDI as well as DIN standards 2862 have a risk class classifications. As you can see there, A, B, and C. This may be something that you're already doing at some of your companies, or it may be something you could consider when you decide how critical is this application that we're considering. Is it a Class A? And a Class A definition typically, as you can see there, has to do with danger to life and limb. Someone may die, as an example, if it's not done right. So steering, brakes, things of that nature that are very critical in that case for an automotive application. Maybe it's a Class B. You know what? This is very critical, but if it's not tightened correctly, no one's going to die, but it's not going to be good. It could lead other problems. And a Class C is, you know what, just kind of that annoying situation where maybe there's a buzz in your dashboard that you can't get rid of. So, you know, I don't know, to me, quality is quality. And obviously you can measure it to determine where you fit and where it's important to have higher levels of tools as well as error proofing. And we can discuss those with you when we meet. Now let's get a little bit into the threaded fastener basics. Really, a threaded fastener, the bolted joint, is the concept or objective is to keep one or two joint members from slipping relative to each other. The fastener itself acts as a heavy spring. The fastener normally stretches during the tightening process to clamp those two pieces together. A couple of different bolt loading terms, tension and shear. When we're putting a bolted joint together, as you can see, we have tension load, right, or shear load. You may have a combination of both in your applications. These are terms and physics that we need to be aware of when we're talking and possibly considering the correct application for a threaded fastener application. So a little bit about a bolt load and how it's defined. You can see the different terms for the bolt itself, such as the grip length, the clamp or the preload area of when we're actually stretching that fastener, creating that tension or tensile in the fastener, and the bearing surfaces under the head and under the nut. And basically, that bolt is trying to stretch as we're tightening it, creating clamp load. Really, at the end of the day, what we're trying to do is not create torque, right? We're trying to create clamp load. We're using torque to get there. So we would say that the goal of the fastening process is not just to meet a torque spec. It's not just to give us a green light, although those are nice. It's not also is to put as much torque possible into the joint. Really what we're trying to do is achieve clamp load and hopefully the correct clamp load that will result in those products staying together both in the plant and when they're in use in the field. So a little bit about clamp load and torque. The clamp force is achieved through the application of torque, as you're familiar with, right? So measuring torque is a lot more feasible than measuring clamp forces, although that can be done. We just need strain gauge type bolts, gauged bolts, maybe a force washer or something of that nature, but it's fairly expensive, but in some cases it's very good to know, so we will do that. But there is a relationship between torque and clamp load. But the relationship between torque and clamp load is dramatically affected depending on friction characteristics. So some basics, some fundamentals. What is torque? Torque is really a twisting moment or result of friction in the product. And when we achieve torque, we're pushing force against a given length. So force times distance. Some engineering units for force times distance are seen right here. Inch ounces, inch pounds, foot pounds, centikilograms, Newton meters, and Newton centimeters. These are engineering units, right? Versus a direct measurement of a geometric tolerance. These are actually engineering units. So some types of torque. Major categories are dynamic, which is the actual torque applied to the joint, to the actual application during the assembly process. Residual torque, which is utilized, it's a very good number to know, by the way. Residual torque is done following the tightening process, and it's a great measurement to see how stable the joint is, right, in the tightening direction. Breakaway torque is in the loosening direction, and depending on the application, that may be also something that is good to know. So as we're applying torque into a joint, we need to consider where is that torque going or how is it distributed. It's very interesting. About 90% of the applied torque is just going in to overcome friction. And some of those friction factors, as you can see there, tolerances, alignment, in other words, holes are not lined up right, surface finishes, materials, different materials, the lubricants, fastener types, different types of fasteners, and the materials within the bolted joint itself. It could be the gaskets, some carpeting, that type of thing. So another way to look at this is this pie chart. So out of 100% of the torque going into the joint, generally speaking, only 10% goes into clamp load, which again is really what we want. The rest of it is absorbed or consumed by thread friction or bearing surfaces under the nut, under the bolt head, those types of things. So here's a clamp load example. Let's say Fastener A, tighten it down at 30 Newton meters of applied torque, no lubrication and a dry bolt. Fastener B, same torque, 30 Newton meters, but now we have oil incidentally spilled on the threads, or perhaps someone is experimenting with this altogether, but it's very important to see the difference. So Fastener A, you can see it follows our previous equation where we have about 50% and plus 40% is eating up by the underhead, thread friction, and so forth, which is only leaving 10% for clamp load, which again is what we want. Fastener B, some oil happened to spill on the threads somewhere or in the joint configuration itself. Now, this is a rough number. It doesn't necessarily mean that the actual clamp load would double, but that is possible, right? So when I reduce friction somewhere, the result has got to go somewhere else. So in this analogy, you can see I've got less friction. Less friction results in more clamp force. More clamp force is okay, but it also maybe is taking that fastener closer to yield. So we need to be very cautious about when these situations occur, or when all of a sudden, geez, we're running a tool that's been running great for years, now we're breaking bolts. Well, something must have changed if we can prove out that the tool is doing what it's supposed to be doing. Another term is called prevailing torque, and that is literally the torque required to turn the nut onto the bolt head before I'm contacting any of the parts. Prevailing torque, there are intentional uses for prevailing torque, which you will see, but graphically you can see the prevailing torque is that after startup, you can see it flattens out within that prevailing torque before the parts mate, and then we shut off. So intentional prevailing torque could be trilobular or thread forming fasteners, could be lock nuts, things of that nature. Very intentional prevailing torque applications, and those are typically for stop loss. You could also say, or it is very true, that a thread locker that is cured also is prevailing torque once it's cured. Before it's cured, it's actually a thread friction modifier, and we'll talk about that later. An unintentional prevailing torque could be that the holes are misaligned, or there's other, like I've got a weldment that's bent out that I'm trying to form in as I'm tightening. So those are unintentional prevailing torques. When we see prevailing torque, and we also talk about this when we meet with you, it's important for us to know more about your application, is that we know that prevailing torque will cause the tool to work harder. So we can see the RPM of a tool will try to be slowing down as the tool is trying to keep up to its spec. We can maybe, because of the RPM drop, if there is, we can see more torque reaction to the operator. And we can also have reduced durability within the tool in the event of a prevailing torque, which again could be just the reality of that joint needs to have prevailing torque. But these are things we look for. In the area of thread lockers, when applied correctly, work fantastic. But the thing we need to be aware of, again, circling back to friction and what a factor that is in how it affects clamp load. As an example, if you had a part that went to the field and all of a sudden the reports back for the field indicate that the bolt's been falling out, well, the evaluations are done. Design engineering determines that maybe we should add a thread locker in there. So they do, which is fine. But again, what they've done, if it started as a dry bolt and now we've got a liquid thread locker, I have now changed that frictional characteristic of the joint, and the threads in particular, and I have less friction, I've got more clamp load. So when you do make these changes, please test. You need to test. The other example shown on this slide is pre-applieds. And pre-applieds also work, right? A little cleaner, I don't have to deal with the liquid, that type of thing. But when you do transition from a liquid thread locker to a pre-applied, it is not a straightforward transition. You just need to be aware of that and do testing if you're thinking about those. So here's a very involved equation for calculating torque and clamp load. I will let you guys maybe see that later. If you want this PowerPoint, it'll be available for you. But we're going to let this slide go and go a little bit simpler one. Torque equals KDF. The K factor, if you see the K factor, that's the one that we deal with the most, really, has to do with the friction characteristics of a joint. But the reason the little cookbook there with the international no is on it, be very careful with just creating a torque before you test anything. Typically, torque may be defined or targeted at about 75% of yield based on testing. So you need to do a number of tests to make sure that that is okay. And then from there, you can establish what plus minus torque tolerance will be acceptable for your application. So things that we should keep in mind about clamp load. We use torque to measure the success and failure of a rundown. But we really want clamp force. So again, a seemingly small change in fastener joint characteristics, as we pointed out, oil on threads, surface finish changes, can result in a large change in clamp force. So why is torque measured? Well, it's easy for us to do. If the friction factors were always consistent, we would always have a direct, always is a big statement, it'd be more common for us to have a direct relationship between input torque and clamp load, but that's often not the case. So how do we measure torque? A couple different ways. If I want to measure dynamic torque, you can see pictures of devices here. The ones in the middle are called rotary torque transducers, where we can put those transducers between the tool and the actual joint, or we can put those between the tool and a threaded test joint. We also have multiple, you can see tester there with has rotaries, so we can run one multiple in one shot and get all those readings in one rundown, right? All dynamic readings. We have internal transducers that are inside our DC tools, or isolated ring gear type transducers. And we also have bench mount transducers, right, which are shown in the lower right in our cart, our torque cart. This is an example, a great example of a test or threaded test joint. This would be often located in a metrology lab or on a cart that's brought out to the line, those types of things. When we get into these threaded test joints, it takes the variables out of the application, and we can actually test the capabilities of the tool separate from the actual joint conditions. They're very useful. This is an example of a measurement display that would read those torque readings that we're getting from the transducers. So a little bit about the threaded joint signature. As you can see, that is just kind of a typical joint signature that we have. Stage one is that prevailing torque area, if there is any. Drawdown, we're pulling those parts together. Then we're actually pulling it into the elastic region, which is where that fastener is starting to stretch. We're starting to create that clamp load. And then if we actually kept turning too far, or as I say, oh geez, I can't believe I just did that. I just went by into the plastic region where the fastener is no longer able to stretch. Now I'm just rotating it, not creating any more clamp load or torque for that matter. So it's very important to realize where you are in that. As I mentioned earlier, typically in the elastic region, you'll want to be 75% of yield is typically a good point to start in terms of a target torque. So we get into a little bit of some definitions further, a little deeper dive into what a joint is, right, between hard joint and soft joint. And the reason for this is it helps us understand characteristics that we would expect for a certain joint. So a hard joint would be a pre-tapped, let's say a pre-tapped hole that a threaded fastener is going into with no prevailing torque, probably no gasketing, something of that nature. Maybe an O-ring though. It's interesting. O-ring joints often are hard joints. But the hard joint occurs basically from snug to less than 30 degrees. We would define that application as a hard joint. A soft joint would be from snug, and it takes me about 2 turns for that to achieve torque. That would be a definition of a soft joint. And those are good characteristics for us to be aware of, or you to be aware of as you're thinking about the applications you have. I mentioned earlier ISO 5393, which was actually put out quite a few years ago to help us define tool performance on test joints. So if I had a test joint that was a hard joint, and then I put that same tool on a soft joint, what type of characteristics does that tool and what kind of torque does that tool put out? That was the intent of ISO 5393. We can also measure the joint rate or the torque rate, right? The change in engineering units per degree of rotation. In other words, how much 1 foot-pound per degree, right? What is that joint rate? And the mean shift is a term that ISIL came up with to help define, especially with clutch torque control tools. When I take that same clutch tool, I put it on a hard joint, I'm putting out 30 foot-pounds. And then if I put it on a soft joint, I'm probably putting less out because the kinetic energy of the tool is being used up in that soft joint as it's tightening. So that direct result, or that term, is called mean shift. Well, we'll talk a little bit about quality. So torque really tells me a tool repeated, actually, right? What can angle do? Angle, and we're talking about the actual rotation of the socket, rotation of the tool spindle. Angle, what we can do is we can audit the entire assembly process, right? We can look for cross threads, soft fasteners, maybe some other product changes. Angle can also help me provide, or the tool provide a better indication of control and clamp load. And even better, it helps us see problems during the assembly process. With a torque-only type tool, I know the tool repeated, but that doesn't mean the bolt didn't stand up and I hit torque. I obviously don't want to ship that. Angle will help me see that. So when we have torque control, we can still target torque, which is, I would say, gosh, 95% of our application, we're targeting torque. But now I can monitor angle, right? So if that's the typical joint signature that you see there, if I had a cross thread where the bolt went down but did not all the way down, it just stopped right here, that curve would go much sharply upward, right, along the y-axis of that graph right there. Or if it was a soft joint, it would tend to go further out on the x-axis. So we can see that. So you can see in this example here, I'm targeting torque, so I need to fall within the high-low limits of torque, but also I've created high-low limits for angle monitoring. So that example and that bolt, or every one of the bolts, needs to fall into that little area, that square, for it to be acceptable and meet quality standards. Where are we watching angle? Angle enable is typically 10% of our target torque, although depending on the joint, we may tweak that a little bit. So basically, I'm going to ignore angle rotation until I'm going to get into more that elastic range of that fastener, which is where I care about, because that's where I'm creating clamp load, right? So I'm going to ignore angle typically on the way down, not always, but usually. And then when I reach those two parts together, the creating clamping force, that's when I'm going to watch angle. And angle, as you can see there, it's a great cutaway of this bolt. You can really see that threads of a fastener are inclined planes. So if I can watch rotation of angle, I have a very, very good predictor of clamp load. So let's talk a little bit about this dynamic and residual torque relationship. Dynamic and residual, there are friction factors that interfere, or I should say affect, both of these. Bearing areas, thread profiles, material hardness, surface finish, coefficient of friction for all of the surfaces, the flatness, under nut geometry, coatings. In fact, we had one of our customers doing high torque work, and the coating on their hardened washer changed, and they went from not breaking bolts to breaking bolts just because the coating on the hardened washer changed. And of course, socket interference. If the socket is up against the part as we're assembling, that's going to have an influence as well. So in the area of manual torque auditing, and in particular residual torque auditing, we've come up with some really neat new torque wrenches. This happens to be a new digital wrench, right? And you can see digital wrenches on the slide there as well. And the new technologies help us with overcoming some of those factors that influence residual torque auditing, such as the friction factor, joint relaxation, and operator influence. So as an example, that first installed dynamic peak there you can see, but with a standard wrench, or a wrench, if I wasn't paying attention using this one, right, I'm going to pull it to get my true static, right, which already I've got a different number. And now I'm probably going to pull it further because I can't stop that fast, and I'm going to leave it at the applied static. So I've actually induced error into this joint by just doing the audit, potentially. This is an example. So as you can see, the operator influence, just by auditing in a residual torque mode, has induced that error. So some characteristics to keep in mind between dynamic and residual. Dynamic or sliding friction is much more consistent than the stack of variables of static or residual torque readings, right? The dynamic torque is a better indicator of the power torque tool, right, and what it's putting out. But a residual audit is a fantastic reference because that helps you understand the joint stability. If you put a joint down at 100 foot-pounds and you come back and you do a residual audit and it's at 75, well, that doesn't mean you didn't put 100 into it. It just means that's a characteristic of the joint. And that could be after time, could be after time temperature changes. It could be shifting, a variety of things. So this is a great example. In particular, I like these slides. This kind of shows you that first curve where we've installed and we've hit our torque and shut off. The curve to the right shows you the residual torque audit and the influences, right? So it's going to take me more torque to get that bolt moving again. Once it moves, that torque drops a little bit, and then it goes back up again because I can't, frankly, stop that fast. This is a great example of a dynamic versus residual. In particular, I like this slide. Hopefully you will as well. This shows the dynamic torque spec of 135 Newton meters. Again, dynamic torque is the amount of torque being applied during the application on the application. So in this case, it's 135 Newton meter plus or minus 15% is the dynamic torque. That same wheel, as it went down the line, when they did a residual torque audit, which they do, again, this is critical joint, the residual spec for the aluminum wheels was 133 Newton meters. So now that mean has shifted down by 2 Newton meters. And it's a much wider spec for residual because they recognize that the variety of stack-up tolerances of friction, there's no way they could have a plus or minus 15% on a residual. They went to plus or minus 24 after a lot of testing and determined that that would be okay. The interesting thing, again, instead of aluminum, instead of, we have steel wheels. Now the residual spec, even though the dynamic target is still 135, the residual for steel, in other words, steel's not going to move a whole lot. Aluminum cold flow is under compression. Steel does not. So at 147 Newton meters is the residual mean, plus or minus 45%, which to me is kind of extreme, but this was an actual case. They attributed much of this huge variation to the powder coat, certainly not the steel. Steel is very stable. So some of the technologies that have come out to minimize these influences that occur during a residual torque audit are smart breakaway angle, where there's logarithms within the digital tool, which are actually minimizing that effect on the residual torque audit. Nice quick little picture of a dynamic cart, dynamic torque testing cart. It's great. You can bring it out to the line. You can do your dynamic audits right there and record everything, as you can see, right on the PC. A little bit in the weeds with metrology and quality, but I thought this slide was kind of interesting, right? There's accuracy and then there's a repeatability. And then ideally, we're both accurate and repeatable. So brief summary. Hopefully, at this point, you've got maybe some questions and things of that nature, but hopefully you're able to define the principles of the bolted joint, understand that bolted joint as a system, understand the function of the bolted joints, can define torque, define clamp load. I don't have angle on there, but define angle, and then also torque measurement. I'd like to say thanks. Open up. And please, we're open up for questions right now, if you would, please. If you have any, please let me know or let us know.
We have a couple already. First question, what are typical engineering specs for torque accuracy?
I'd say for dynamic torque, I would say plus or minus 10% would be fairly common. We get into plus or minus 5%, again, dynamic torque for powertrain. Engines and powertrain seem to be more than that plus or minus 5% for dynamic torque. And then residual specs are usually open from there as well, a little bit wider.
Perfect. Next question, do you offer any on-site training?
Yes, we do. So I'm sorry, I didn't know if Dave's going to answer that. Yes, we absolutely do. We'd be happy to work with you on that. Just please get in touch with your Rhino Tool House sales engineer, and we'll talk it over. And determine what would be the best approach, meet with you. Thank you.
All right, we'll give it just a couple more seconds here if anyone has any other questions to type them in the chat box. Yep, we got a couple more in. Can you do a joint study?
That would be possible. I think we definitely would want to understand the objectives of that joint study, but I would say yes.
Awesome. Someone is asking, can I re-see this video? I was interrupted during the program, and Greg, yes, absolutely. We upload all of our videos that we have throughout this entire demonstration to our Rhino Toolhouse YouTube page. So in a few days, this one will be uploaded as well. Do you offer any other torque training?
I'm not sure what other means, but we certainly, this was a very condensed version of our torque seminar, just given time constraints, but we certainly would put on a torque seminar either offsite or within your building. And again, that would be something to talk over with your sales engineer.
But yes, we can, to add to that, we can certainly do dynamic torque testing on site. We do residual torque audit with your guys' quality department or manufacturing teams. But we can also just do a theory of fastening with more of an engineering aspect as well.
Okay, and off of that as well, would you be able to talk more into the tool hierarchy and types of tools to use and why?
Yeah, so thanks for the question. 100%. When we sit down with you and kind of reflecting back on the VDI or DIN standards, those are the kind of questions we need to ask is, what levels of quality are you trying to achieve? Where are you at now? Where do you envision going? And that's such a great point. We will match the technology to where and hopefully meet and or exceed your objectives of what you're trying to do.
Perfect. Are you able to come in and walk my line to make suggestions on torque improvements?
Yeah, absolutely.
If you're in Hawaii, we can be there very quickly. but yes, we can do that.
Aloha.
All right, and then another administrative question. Can we receive the presentation via email? Brock, absolutely. Once we get it uploaded, I can send this out via email to you as well. Give it a couple more seconds for any other questions.
That all right?
Are we back?
And you're back.
Oh yeah, but I don't know if people heard what I just said. Well, this presentation today was about 30 minutes, and so it was very, very condensed. And so normally these presentations could be anywhere from an hour to all the way to a half a day. So we can customize those based on you guys' requirements.
Awesome, and it looks like we have no other questions. So with that, I will throw it back to you, Dave.
All right.
Very good.
Great.
Thank you.
Thank you everyone for attending. And as I mentioned, please contact your local Rhino Toolhouse sales engineer if you're looking for any more information on bolted joints, on fastening, or just overall manufacturing and assembly. We'd be happy to take a look and help you guys out. And please join us tomorrow as we will be taking a closer look at electric pulse technology in an Industry 4.0 environment with our partner, DeSuter. Thank you again.